Hello, I am the presenter Wonjae Choi. In this presentation, I will proceed with a presentation about the paper titled Embodied CoT Distillation from LLM to Off-the-Shelf Agents. The order of the presentation is as follows. First, the introduction section. I am PhD student in the machine learning lab directed by Professor Woo Hong-wook. Our lab's research broadly focuses on advanced reinforcement learning techniques and their applications across various domains. Specifically, we work on developing multitask and meta-RL methods that allow reinforcement learning models to handle diverse tasks efficiently and rapidly adapt to new, previously unseen scenarios. Additionally, we engage in research on multimodal reinforcement learning and imitation learning, aiming to create agents that integrate multiple modalities, including visual, texture, and sensory inputs. This approach ensures that the agents can reliably perform tasks even in environments they have not previously encountered. Another important area of our research is sample-efficient offline RL, where we seek to address the challenge of effectively training RL models when limited data from the target environment is available. To achieve this, we explore various approaches that enhance sample efficiency, such as model-based RL techniques and advanced offline RL methodologies. Lastly, our work includes skill-based learning, which investigates how reinforcement learning agents can swiftly master complex and long-horizon tasks. This is accomplished by decomposing these new and challenging tasks into simpler, manageable skills, allowing for quicker acquisition and robust performance across diverse tasks. Again, I'm Wonjae Choi. If you have any questions or would like to discuss research topics further, feel free to reach out to me via email address. And my research focuses on reinforcement learning and embodied AI. Today, I'll be introducing the paper titled Embodied CoT Distillation from LLM to Off-the-Shelf Agents, which is presented at the International Conference on Machine Learning called ICML. Let's delve into the abstract of my paper. In this slide, I present the background, objectives, and key contributions of my work. First, embodied agents operate with partial observations, meaning they only perceive limited information about their environment. This partial observation makes decision-making more complex, much like in real-world settings. Second, there is a growing trend of leveraging LLMs, large language models, for both reasoning and execution of tasks. By interpreting task instructions and using the limited sensory data available to the agent, LLMs enhance overall task performance in dynamic real-world environments. Given these developments, our objective is to achieve a robust SLM, small language model-based policy that can be deployed on capacity-limited, off-the-shelf devices while retaining capabilities similar to LLM-based policies for embodied task planning. Lastly, the contributions of this work are summarized as follows. We introduce DEDER, a novel framework designed to distill the reasoning abilities of LLMs into smaller policies suitable for capacity-limited, off-the-shelf devices. And we propose a two-tier policy hierarchy that decomposes the embodied reasoning process, enabling systemic knowledge transfer to achieve robust SLM-based policies. We develop a data construction process using LLM-generated rationals tailored to embodied tasks, exploring in-context learning and self-verification methods. Next, we implement an embodied knowledge graph and a prompted attention model for SLM-based policies, improving rational quality in ever-changing environments and facilitating rapid task planning. Through extensive experiments on Alfred, we demonstrate that DEDER effectively delivers strong zero-shot performance for previously unseen embodied tasks, or while maintaining computational efficiency. Now we move on to preliminary section. This slide explains what embodied AI is. Embodied AI is a research area centered on integrating artificial intelligence into physical situated systems, such as robots or machines, that can perceive, act, and run within dynamic real-world environments. By embedding AI in tangible contexts, this approach shifts the focus from mere data processing to active sequential interactions, enabling agents to gather experiential knowledge and adapt to changing conditions. These systems employ sensors and mobility to explore their surroundings, learn through experience, and tackle complex tasks. And they drew upon computer vision, natural language processing, and reinforcement learning to handle multifaceted challenges that demand a nuanced understanding of both physical and abstract domains. By doing so, embodied AI aims to expand the scope of artificial intelligence, guiding it toward versatile, adaptive performance in dynamic real-world scenarios. This slide introduces two representative simulators for building embodied AI environments, AI Tutor and Habitat Sim. AI Tutor is built on the Unity 3D game engine, featuring four main environment categories: kitchen, living room, bedroom, and bathroom, and offering 120 photorealistic 3D scenes. It supports various agent types and enables tasks like object navigation, rearrangement, and manipulation through direct interaction in the environment. Similarly, Habitat Sim is a highly extensible 3D simulator that provides advanced physics and large-scale indoor datasets. It supports diverse embodied AI tasks, including navigation, instruction following, and question answering, making it ideal for research requiring realistic, dynamic indoor environments. In this slide, we will look at representative embodied task benchmarks that build upon the previously introduced simulators. Alfred is an environment for embodied AI tasks constructed on the AI. In this slide, we will look at representative embodied task benchmarks that build upon the previously introduced simulators. Alfred is an environment for embodied AI tasks constructed on the AI tutor framework. Using natural language directives and visual information, it emphasizes real-world domestic scenarios with complex goals, multiple stages of interaction, and a high level of environmental understanding, allowing agents to demonstrate advanced reasoning and action planning. Now I will introducing some papers related to embodied AI and domain adaptation in RL. First paper is simple but effective clip embeddings for embodied AI. For the first time in the field of embodied AI, clip embeddings were applied to various environments and tasks, replacing the previously used ImageNet pre-trained embeddings. Experimentally, it was demonstrated that clip embeddings effectively contain the primitive features required for diverse complex vision tasks. Second paper is Jetson zero-shot object goal navigation using multimodal goal embeddings. It utilized the clip space to address the problem of zero-shot transfer across modalities in visual navigation tasks. And it proposed an algorithm for zero-shot transferring and an agent trained on image navigation task to the object navigation task. Third paper is Zero Experience Required Plug-and-Play Modular Transfer Learning for Semantic Visual Navigation. Basically, visual navigation tasks are distinguished based on the goal modality, presenting the issue of needing to retrain the policy for each target task. To address this, this paper proposed an algorithm capable of zero-shot transfer across 5 different goal modalities, achieved through the training of multimodal goal embeddings. And in this slide, I will introduce some embodied AI researches. With the recent research of large language models that demonstrates strong performance on diverse language-based tasks with large-scale parameters, researchers are increasingly turning to these models for complex, high-level task planning in the embodied AI domain. This has led to a number of LLM-driven approaches designed to tackle embodied tasks. Some representative studies include SeiCan, PalmE, and LLM Planner. First, SeiCan combines the feasibility of skills proposed by an LLM with a value function learned within a specific environment, resulting in executable plans for physical environments. And second, PalmE integrates a vision input module into a pre-trained LLM to optimize it for multimodal embodied tasks. By training through text generation on a given dataset, It learns to produce task plans that account for both visual and linguistic information. And LLM Planner retrieves example trajectories, selects a few samples that best match to the current tasks using text embedding similarity, and uses them as an in-context prompt for the LLM. The LLM then generates a sequence of skills for target tasks. A low-level policy executes each skill step by step, interacting directly with the environment to complete the task. Starting from this slide, I will introduce the methodology proposed in my paper. In the DEDER framework, we use MDP-featured chain of thought prompting to extract rationals from large language models and then effectively distill these embodied reasoning capabilities into smaller models. First, the framework goes through a rational dataset construction phase. Here, we employ MDP-featured in-context learning, where other specific queries are used as prompts to create a dataset of rationals. And then we enter the policy distillation phase by establishing an SLM-based policy built around a two-tier hierarchy based on embodied knowledge graph. Within this structure, a reasoning policy is trained to generate single-step CoT rationals optimized via behavior-based contrastive learning. A planning policy then uses those rationals as guidance, inferring action plans through CoT prompting. Finally, in the deployment phase, we test our distilled SLM-based policies in unseen environments under a zero-shot setting. Here we vary task descriptions, object positions, and indoor scenes, allowing us to assess how robustly the distilled policy adapts to new conditions. And then we will explain the rational dataset construction phase in detail. We begin by incorporating Markov decision process features such as goal, state, observation, action, return to goal, and sub-goal into the reasoning process. These elements serve as justifications or hints that illuminate the rationale behind each plan, enabling us to effectively distill the embodied reasoning capabilities of an LLM into smaller models, ultimately forming an SLM-based policies. Within MDP-featured in-context learning, we sequentially prompt the LLM with other specific queries and continually update the in-context examples in retrieval-augmented manner. To ensure that the extracted rationals remain consistent with the corresponding action plan, we also use the LLM as a verification function throughout this process. This slide shows an example of MDP-featured in-context learning data. Next, I will explain the policy distillation phase in detail. To distill the reasoning capabilities of the LLM into SLM-based policies using the rational dataset, we adopt a two-tier policy hierarchy. First, the reasoning policy infers a set of rationals based on current observation, the task description, and information stored in an embodied knowledge graph. Second, the planning policy then uses those rationales to generate final action plan. Here, the embodied knowledge graph functions as an internal component of the SLM-based policy, holding essential environment details. Since the agent actively interacts with its surroundings and accumulates information relevant to completing tasks, it is crucial to manage this knowledge effectively for prompting the SLM-based policy. The reasoning policy supports multiple rationales in a single-step chain of thought inference by combining prompted attention with an encoder-decoder architecture, all of which is optimized through behavior-based contrastive learning. Lastly, the planning policy uses the rationales produced by the reasoning policy to predict the next plan, enabling the agent to systemically proceed toward its goal. Now, evaluation section. We conduct our evaluation in the Alfred environment. We start by collecting 312 trajectories for our expert dataset and then organize our evaluation tasks into 4 categories based on their similarity to the tasks in the expert dataset. First, train category. It uses tasks identical to those in the expert dataset. And scene category keeps the same tasks but randomizes the starting positions of objects that are irrelevant to the tasks. Next, unseen spatial category randomize the placement of all objects in the environment. Last, unseen category presents new tasks and indoor scenes not included in the expert dataset, making it the most challenging category. And we use 2 different metrics following the Alfred evaluation protocol to assess performance across all these categories. We evaluate the performance of embodied task planning by measuring each policy in a zero-shot scenario. Our approach DEDER achieves robust performance on both success rate and goal condition success rate metrics across all test categories, outperforming the LLM-based method by 21.6% in success rate and 12.3% in goal condition success rate. It's especially notable given that the LLM-based method relies on PAM with 540 billion parameters, which is about 2,700 times larger than DEDER. Despite its much smaller size, DEDER still achieves a significant performance improvement. Moreover, when compared to baselines of a smaller parameter scale, DEDER shows improvement of up to 27.6% in success rate and 12.6% in goal condition success rate, highlighting its strong effectiveness for embodied task planning. This is now the concluding section. In conclusion, we introduced DEDER, a novel framework designed to distill the advanced reasoning capabilities of large language models into more compact small language models. This approach enables complex embodied tasks to be executed effectively on device-constrained platforms. Looking ahead, we plan to enhance the framework's ability for few-shot optimization, particularly in domain-shifted settings, to further explore and expand the versatility of LLMs. Thank you for listening.